In the last video, we have learned the problem definition of the phase estimation algorithm. Furthermore, we have also derived its quantum circuit by a step-by-step process and done all the mathematics. In case you have not watched the last video, then I highly recommend watching it first. Now, in this video, we will be doing an example of phase estimation by hand. Solving an example by hand will clear all our doubts and hopefully will answer all our questions. So let's start. Given a unitary matrix U equals to minus iota times bra 0 cat 0 plus iota times bra 1 cat 1 and an eigenvector cat v equals to cat 0, estimate two bits of theta belongs to 0, 1 such that unitary matrix times eigenvector is equals to eigenvalue, which is either constant raised to power 2 pi I theta times eigenvector. So basically we have to estimate this theta of the eigenvalue in this example. Before solving this example, let me clarify some of the basics. First of all, this is a fancy notation or a bracket notation to write a matrix. So this matrix is a 2 by 2 matrix. Basically my unitary matrix according to this notation is equals to minus iota 0 0 plus iota. So this is my unitary matrix. Secondly, although I am finding theta of the eigenvalue, but because this phase estimation use an oracle, where oracle knows the answer, and then we ask oracle the eigenvalue and then use it in our calculation. So to solve this by hand, I have to know the eigenvalue beforehand. So my eigenvalue, this one, is equals to minus iota. So I will be using this eigenvalue throughout my calculation. So now we can start. We start by creating our quantum circuit. Our quantum circuit will have two registers. The size of first register depends upon how much we want to estimate. In this case we want to estimate 2 bits of theta. So the size of the first register will be equals to 2 bits. Let's say it m. In contrast, the size of second register depends upon our unitary matrix and eigenvector size. And because our unitary matrix is 2 by 2 matrix, so in this case the size of second register is also 2 bits or 2 qubits. So let's say this our n, which is also equals to 2. So now I can create my quantum circuit. My quantum circuit has two registers. First register is of m qubits and which is equals to 2, and it takes input of cat 0 0. The second register is of n qubits, where n is also equals to 2, and it takes input the eigenvector. So let's write it here, cat v, which is equals to cat 0, but we don't have to write cat 0. Now I apply Hadamard gate on the inputs of the first register. Based upon the outcome of the Hadamard gates, I apply unitary matrix on my eigenvector. So in case my first register, first qubit is 1, then I apply unitary matrix on the eigenvector. Similarly, if my second line of the first register has 1 on it, then once again I apply unitary matrix operation on the second register, but this time I'm scaling my unitary matrix. So scale of unitary matrix on the second register. Afterwards, I apply reverse quantum Fourier transformation on the first register. And then I measure my first register. Now, the result of measurement is not theta, but a value y. So I get from here a value y, where my theta is equals to y over 2n with high probability. In the last video we have calculated the probability of this. So I know that my m is equals to 2, so at the end my theta is going to be y over 4. Now let's divide this circuit into different stages and see the outcome of each stage. So let's call the first stage of this circuit as cat psi 1. The second stage of this circuit is cat psi 2. The third stage is cat psi 3. And the final stage is cat psi 4. My cat psi 1 is equals to cat 0 0 and eigenvector v, which is also equals to cat 0, but I'm writing here v for the time being. My cat psi 2 is that I apply Hadamard gate on the first register while keeping the second register untouched. So the result will be 1 over square root of 2 raised to power 2 summation x is equals to 0 to 3 and cat x. And then I have my eigenvector here. This is the outcome of my cat psi 2. To understand it better, I can expand this. So let's expand this. My cat psi 2 will be 1 over 2. You don't have to write square root and 2 raised to power 2. I just simplified it. And then I will have here cat 0 plus cat 1 plus cat 2 plus cat 3. And my second register has cat v, which is my eigenvector. Now I have to calculate my cat psi 3. My cat psi 3 is that I apply a unitary matrix operation on my second register. So let's first write it in general form. It will be like 1 over 2 and x goes from 0 to 3, and here I will have cat x. We have discussed in the last video that what this operation is. And basically in this operation it simplifies to that whatever the value of x is in the first register, in the second register we power the unitary matrix with that value. Why this operation is like this, we have discussed that in the last video, so you can go back and watch that. So here we will have unitary matrix raised to power x, and then we will have our second register of vector v. Whenever we apply unitary matrix raised to power x on cat v, our result will be eigenvalue. This unitary matrix will be replaced by the eigenvalue raised to power x times cat v. So this is by the definition of eigenvector and eigenvalue. So this thing will be replaced by 1 over 2 summation x is equals to 0 to 3 cat x, and here I will use my eigenvalue, which is minus iota raised to power x cat v. Now I can use the concept of phase kickback. So I will use the concept of phase kickback, and this phase I can associate with the first register. So therefore my cat psi 3 will become 1 over 2 summation x from 0 to 3 minus 1 my phase minus iota my phase raised to power x cat x. Because we are only measuring our first register, not using the second register anymore from this point, therefore I don't have to write second register now. So I'm not writing second register anymore. Let's expand this and write it fully. So I don't need to keep my other stages. My cat psi 3 is equals to 1 over 2 and minus iota raised to power 0 cat 0 plus minus iota raised to power 1 cat 1 plus minus iota raised to power 2 cat 2 plus minus iota raised to power 3 cat 3. Which simplifies to 1 over 2. This will be 1, so I have cat 0 here, plus this will be minus iota, so I will write minus iota cat 1. This will be equals to minus 1, so I write minus cat 2. This will be equals to plus iota, so I will write here plus iota cat 3. So that's my cat psi 3. To calculate cat psi 4, I have to apply a quantum Fourier transformation inverse on cat psi 3. So my cat psi 4 is that I apply a quantum Fourier transformation conjugate transpose on cat psi 3, or basically the first register of the cat psi 3. So let me write what is quantum Fourier transformation, and also let's calculate its inverse together. So quantum Fourier transformation is equals to 1 over square root of 2 raised to power 2. Here I will have 1, 1, 1, 1. In my first row, second row I will have 1. Second entry will be omega 4 raised to power 1. Then I will have omega 4 raised to power 2 and omega 4 raised to power 3. Third row will be 1, omega 4 raised to power 2, omega 4 raised to power 4 and omega 4 raised to power 6. Then the last row will be 1, omega 4 raised to power 3, omega 4 raised to power 6, omega 4 raised to power 9. However, these omega represent a modular function. So you can say that omega 4 raised to power k is same as omega 4 raised to power k mod 4. Using this, we can simplify many of the entries. So these entries are fine, this is fine, but this is not fine because 4 mod 4 is equals to 1. So I don't need a power of 4 here. Similarly, 6 mod 4 is equals to 2. Therefore, I can replace this 6 and this 6 by 2. So let's replace this 6 by 2 and also replace this 6 by 2. And lastly, that 9 mod 4 is equals to 1. So I replace this 9 by 1. So now I have my quantum Fourier transformation matrix which is simplified also. However, I have to calculate the conjugate transpose of this matrix. How to calculate conjugate transpose of this matrix? I have to take transpose and also I have to take conjugate. So let's try to do that. Now, if we just look at this matrix without considering conjugate, then it looks like this matrix is symmetric because we have omega square here, omega square here, we have omega cube here, we have omega cube here. So it looks like a symmetric matrix. But when we take conjugate, then it will no more symmetric matrix. So I'm not taking transpose of it because transpose of it will be the same matrix. I'm only concentrating in calculating conjugate of this matrix. That means I will make iota negative in all of those terms. To do that, let's consider the unit circle. This is my unit circle. Here I have 1, here I have minus 1, here I have iota, and here I have minus iota. Now, omega 4 is defined as Euler constant raised to power 2 pi iota over 4, which simplifies to Euler constant raised to power pi by 2 iota. So my omega 4 raised to power 0 is here. According to this definition, my omega 4 raised to power 1 is here, and my omega 4 raised to power 2 is basically minus 1, and my omega 4 raised to power 3 is minus iota. Okay, so if I have to calculate an inverse of omega 1, then I can go to the other direction. For example, if this is my original direction, and if I take the negative theta, that means if I have a minus here, then my theta will become negative, so my direction will reverse. I will travel this direction. So this is my original direction for omega, and this will be my conjugate transpose, conjugate direction. So this will be my inverse direction. So if I get omega 1 by traveling a distance of 1 in this direction, and I will get, if I travel the same distance in the other direction, I will get minus iota. So this will become minus iota, or omega cube basically. So let's say this will become omega minus iota. Similarly, omega square is that I travel 2 units this direction, whereas to find inverse I have to travel 2 units this direction. In both cases I will get minus 1. So my omega square, I'm just calculating the conjugate transpose by the way, my omega square is going to be minus 1. My omega cube in this direction is minus iota, but I have to calculate its conjugate. So I will travel this direction and I will get a positive iota. So I will have here positive iota, or omega 1. Omega square in both direction is equals to minus 1. I will get here minus 1. Omega in this direction is iota, in this direction is minus iota, so I will have here minus iota, and then omega square is always minus 1 in both directions. Omega cube in this direction is minus iota, whereas in this direction is iota. So I will have here iota, and similarly omega square in both direction is same, which is equals to minus 1, and omega 1 in this direction is iota, in this direction is minus iota, so I will get here minus iota. So this is my conjugate transpose of quantum Fourier transformation. Now to calculate ket psi 4, I have to multiply my ket psi 3 with this matrix. So let's do that. My first entry of the vector is 1 because ket 0 is multiplied by 1. So I write here 1. The second entry is minus iota. So I will have here minus iota. Third entry is minus 1. So I will have here minus 1. And the final entry is plus iota. So I will have here iota. My ket psi 4, basically this is no more, and also I have this 1 over 2 here. So my ket psi 4 is that I have to multiply 1 over 2 with this 1 over 2. So my final result will be 1 over 4 times 0, 0, 0, 4. Because everything else will cancel from each other, and which is equals to ket 3. Now if I measure my y, my answer will be equals to 3. So my y after measurement will be equals to 3. As we know that our theta is basically y over 2 raised to power m, where my m is 2, so it's y over 4, as my y is 3, so theta is equals to 3 over 4. That means my eigenvalue lambda will be equals to Euler constant raised to power 2 pi I times 3 over 4. That's my theta 3 over 4. And this simplifies to minus iota, which is our correct eigenvalue. And that's it. We have done it. See you next time. Bye.